Good morning. We have a special session today. Um, yes, everybody's eyeing Philip curiously. Our special guest today is Philipp Nazari. And I was so fortunate to advise him for his bachelor thesis a while back. He is now studying at ETH in a master's course on machine learning. And now I'll take a bit of a detour and say why I invited Philip. And this will take a moment, so if you want, you can take a seat, but you don't have to. Huh? So I wanted to tell you a little bit about the habits and the peculiarities of parts of how the scientific machinery works. And for that, I'm going here to this Google Scholar page, which has become, the de facto, I would say, workhorse search engine and so on that people use to find interesting work. And but it has other things also. So up here on the top left, there is something called metrics in the English version. And this looks at different publication venues across the sciences. Who knows what an H-index is? Okay, so H-index is short for Hirsch index, after Hirsch, who proposed it. And it is a metric, it is one metric both for scientists and for publication venues. So, as kids, we used to play these quartet games where you had to say, how many horsepower does a car have and how fast does it accelerate and so on. And many think of this as the horsepower of scientists. Yeah? So you can also say H for horsepower. Okay. Now, so I can give you the definition, and and then it can give a few caveats. So, as you know, scientists publish, and hopefully this work gets read. And if others find it useful, and are building on it, then they are supposed to cite that prior work. And if they do so, then these citations are counted. And an H-index of H means that there are, of a scientist, means that the scientist has published at least H papers with more than H citations. Similarly, for journals, there is the H5 index, which says how many papers have been published in the last 5 years that have been cited more than H times. Okay, now the caveat is this depends very much on the field. Yeah, so when I say horsepower, it is with a couple of disclaimers, like if you look at cars, yes, the horsepowers matter, but the weight also matters. Yeah, you have to put these things into relation. And for scientists, this means if somebody is working in a small field, if there are 10 people in the world who can understand this paper, let's say that's often the case in pure math, then there is an upper limit of, this paper can only ever reach 10 citations. And vice versa, people working in nuclear physics or working in astronomy, they have these papers with the very impressive list of authors. Yeah? You can literally have 200 or 300 authors, and then these papers get cited a few 10,000 times, and then each of the hundreds of authors gets the credit for this. Yeah? So you need to normalize this a little bit by how long are the list of authors and how big is the respective scientific field. And I'm mentioning it because scientists fret about this a lot. So like in search committees for professorships, people secretly or overtly, they always look at the Google Scholar page, and then if you know nothing about the field, and if you didn't understand a single of the papers that the person has written, then you can always say, yeah, but he or she has an H index which is too higher than that of the other candidate, and so the argument in itself is kind of ridiculous and worthless, but it does play a great role in the real world, so yeah, I think what really matters when it comes to looking at people and their work is what are the actual contributions, and how interesting, how relevant are the papers, actually not just counting H-index. That said, it's a much better metric than the previous one, which was just a number of publications, because this was an encouragement for people to just publish worthless trash. The more the better, right? So you could have 500 publications better than 300, so that's a great incentive to just publish more trash. Yeah? So in that sense, H-index is a kind of robust statistics. It's a lot better than number of publications. All right, so we have this for journals also. So here 488 means that there are at least 489 papers which have been cited more than 488 times, published in Nature in the past 5 years. Okay, and Nature, yeah, is a journal covering all of the sciences, and it's, Nature and Science, I would say, are the two most important general purpose scientific publications. But then let's look here. This is IEEE Conference on Computer Vision and Pattern Recognition, or CVPR for short. And this is essentially machine learning applied to image analysis. It was different 20 years ago. So 20 years ago, machine learning was just a niche in that field, and people were building impressive pipelines by hand. But nowadays, it's really just applied machine learning. Then the New England Journal of Medicine, it's the most important medical journal. You would expect medicine up here because maybe not so much at age 23, but when you get a bit older, literally everybody worries about their health. So everybody cares about medicine. So it's a really, well, for humankind, a really important topic. It's also a topic in which there is a lot of money, a lot of interest. Then this one tends to have, this one is a bit bio-oriented. This is medicine. Here is machine learning again, neural information processing systems, or NeurIPS for short, material, cell. This one is amazing. ICLR, ICLR for short. This thing did not even exist 10 years ago. I think it has been founded around 5 years ago, and out of nowhere, made it on the top 10 of this how important are journals across all fields of science. All right, then this is a medical association, not the mathematical association. And here is again machine learning applied to computer vision. And here is again machine learning. So we have seen in the top 20 journals as measured by citation count, the top 20 journals across all fields. In the last 5 years, machine learning has 5 out of these 20 top spots. So it really says, machine learning is, it's really causing a revolution in the sciences. Now, these conferences are interesting beasts in themselves. The larger ones, they have around 10,000 participants. I think there's also a cap on that because somehow the conference centers and the poster sessions and so on, they cannot handle that. They cannot handle more than that. Each year, to each of these big conferences, around 10,000 papers get submitted. And out of these 10,000, around 8,000 are rejected. So based on a peer review process, which always has a large fraction of chance involved. So we call it the reviewer roulette. You throw a dice and you get 3 or 5 reviewers, and they may or may not be knowledgeable, and they may or may not be malicious, and they may or may not, okay, there's knowledgeable, but there's also experience, you know, to put things a bit into context and so on. And well, the quality of reviews is mixed, but still, in expectation, most papers that make it are at least not terrible. And you know, vice versa, that doesn't really hold. So there are very good papers that get rejected for the wrong reasons. And there are famous examples of really important papers that had to be submitted, you know, 3 or 5 times in a row until they finally made it. And then eventually they became really, really important for a field. So I'm saying that because, you know, in this field or a different field, you know, when you get your first rejection, people tend to take it very personal, yeah, and don't, yeah, it's okay, that happens, and you know, just try again, and if your work, you know, is trash, hopefully it will keep getting rejected, but I trust that your work probably was decent, and then, you know, it will make it eventually. But it's fiercely competitive. And because of what I mentioned earlier, you know, how people get positioned in academia and so on, this also matters. Yeah? And as a consequence, there are many people, you know, who would sell their grandmother, you know, to have a paper in one of these big conferences. It's extremely competitive. And so I'm proud if from our university, you know, I'm proud if PhD students manage to publish there. I'm especially proud if master students manage to publish there, which happens much, you know, rarely, right? It's as I said, it's extremely competitive. And I'm particularly proud when bachelor students manage to get a paper in one of these conferences. And that really is a rare feat. Well, Philipp Nazari is one of those who managed. Philipp studied for his both physics and mathematics bachelor here. And as I said, now currently is at ETH. And he is the first in a number of presentations you will see from other people who have previously sat on one of these seats and who now are somewhere in the world. And there's a selection bias, you know, they all do something with machine learning because otherwise they don't match the lecture. But amongst those who were sitting in one of those seats and now moved on, you know, to other places and roles in the world, we will have a few more speakers this semester, including Letizia Pachalabescu, who will be here on December 10th. I say more about that another time, but I think that will be a great presentation also. Yeah, and now Philipp's work is a good match for where we are in the lecture right now, because in our toy examples of what do neural networks do, we have mostly been discussing neural networks for classification, neural networks for regression. And well, the bane of neural networks is that this design space is so large. But the boon of neural networks is also that the design space is so large. Yeah? So you can build architectures to do almost anything, including things much different from classification and regression. And Philipp will give you an example of that today. And with that, I would like to ask you to give Philipp a warm welcome.
Can you hear me? I had test. Okay. Yeah, well, thank you very much, Fred, for this very warm introduction. So I will not have to introduce myself anymore. But maybe I want to start with a high-level comment. I think I'm here today for 2 reasons. First of all, as Fred said, I'm going to give you a high-level introduction and a high-level overview over autoencoders, which are the specific kind of neural networks, which you can use for a bunch of reasons. But the other reason is that I think because machine learning is such a new field and such a fast-paced field, even you as, or we as like undergraduate or even graduate students, we can actually do meaningful research in this field. I think we all are, we're probably, or most of us have a physics background. And in physics, it's very hard to publish, especially when you're like an undergraduate or graduate. I think it's probably impossible, I don't know. But in machine learning, it's actually possible. So I would encourage you to keep, of course, only if you're interested, to keep following this subject, because it's like you can actually do research and you can think about doing a bachelor or master thesis or whatever on machine learning. And if you're fortunate enough, if you work hard, and also if you're lucky, yeah, you actually have the possibility of contributing to cutting-edge research. Most of my talk today will be focused on the background of the paper Fred talked about, and the paper is called Geometric Autoencoders. What you see is what you decode. And if you have your laptop or your iPad, you can open it up if you want, because I will not go into great details. And if you want to follow some of the proofs, which I will only sketch, you can just follow them in the paper, as you want. Okay. That's the pen, that's not the chalk. Yes. Okay, throughout this talk, I will denote by curly X. First of all, also excuse my bad handwriting. If you can't read anything, just let me know. I will tell you what I'm trying to say. Okay. We let curly X and Rn be a data set. Of m samples, and we let X in R, I think it's n times m, be the data matrix. Where you just stack the data points into a matrix. And now, if we look at this data, in real life, oftentimes for machine learning applications nowadays, this data is usually or can be very high dimensional. If you, for example, think about image processing and you only have an image with 10 by 10 pixels and 3 color channels, then this image already represents a point in a 300-dimensional space, which is very high dimensional. Or if you look at modern like biomedical data sets, where you can, for example, encode gene information or something, this data set will also typically have a couple of 100 dimensions. And now there's a bunch of problems that come with having such a high-dimensional data set. First of all, when processing this data set, it will take a lot of space to store. It will be slow to process. Okay, those are two technical reasons. But there's hope, because oftentimes there's this hypothesis, I think it's called manifold hypothesis, that like real-world data sets usually lie on a lower dimensional manifold. So the intrinsic dimension of the data set is lower than the dimension of the space the data set actually lives in. So it's reasonable to assume that we should be able to somehow reduce the dimensionality without losing too much information. So that's the good message. But there's also another reason why we would actually maybe, besides like the speed and storage reasons, that we would maybe want to reduce the dimensionality of the data set. And that's because of how we humans work. So if we want to understand a data set, we cannot look at it in 300 dimensions, but we can only think in up to 3 dimensions. And if we have a biomedical data set and we want to, for example, identify cancer patients or something, as humans, we want to look at the data, so we have to project it down into a lower dimensional space. So all of these are reasons why we would like to kind of create lower dimensional embeddings of high dimensional data. And I think in the beginning of the lecture, you've already talked about PCA, right, which is a linear dimensionality reduction method. And I want to argue today that autoencoders can be thought of as a nonlinear generalization of PCA. And you will see later what I mean by that. But I maybe first want to start with a quick drawing. Okay, and I will, we look at R2. Okay, and let us assume we have a 2-dimensional data set, which looks like something we call a Swiss roll. Okay, so the data set is sampled from this from the Swiss roll. And now you want to reduce the dimensionality of this two-dimensional data set to one dimension. What PCA would do, it would look for an axis of highest variance. And for example, it would be this axis. And then it would orthogonally project the data points onto this one-dimensional subspace, or affine. Here it's like a linear subspace if it goes through the origin. But the problem is with PCA, like the structure of this data set is somehow intuitively nonlinear, right? So if you project it down, you will actually lose the information that these points lie on the Swiss roll, but yeah, you will lose all information that's orthogonal somehow to the linear subspace. And now it would be really nice if what we could do would be the following. We could kind of fold a one-dimensional space into the data. If we could then map the data onto this one-dimensional space, on this, it's like on this embedded on this embedded line, and then we could actually unfold. This space, and then we have our points like they are like on a chain. You just have your pearls like this, and arguably this would way better capture the internal structure of the dataset, right? Because you're interested like how do they follow to each other? What's the order of these points? And now autoencoders actually allow you to do something like this. Okay, so but obviously for this you need like this is not a linear process, right? Okay, so now that we've seen this motivation, I want to provide the definition of an autoencoder, the mathematical definition. Everything today will not be too rigorous, but I will try and be as precise as possible and necessary. Okay. Yes. Okay. So the definition of an autoencoder goes as follows. An autoencoder is a neural network. I will abbreviate this by NN. The network goes from Rn into Rn. Okay, so from the dimension stays the same, and it consists of two parts of an encoder E, which goes from Rn into some RL. Okay, now the dimensionality changes of the space, and a decoder, which basically maps back from RL into Rn, such that the neural network is exactly D after E. Okay, so first you map into RL, and then you map into Rn, and typically, and this is, we will see later why, but typically L is way smaller than N, and you can already see how this could potentially allow us to lower the dimensionality of the data set. Okay, and now it is trained, the network or the autoencoder is trained to minimize the loss, or the so-called reconstruction loss. The reconstruction loss such that, I'm trying not to stand in the way, such that E and D, okay, we want them to be the minimizers over all possible E prime, D prime, which can be, which are again pairs of, which are again encoder-decoder pairs, which can be like constructed by twisting the weights and biases of the network, right? So you want to minimize over the weights and the biases, basically. And what you do, you minimize the residual between the data and the output of the network in the L2 norm. Okay, and I will take a minute to ponder on this. Right. So an important thing to say here is that the encoder and the decoder are in general not linear. If we don't, or need not be linear, if we don't pick linear activation functions, for example, if we pick a ReLU or whatever, these were non-linear functions. So we can already see how this could potentially be more powerful than PCA, which relies on linear maps to map down to the lower dimensional space. And second of all, if we look closely at this loss, what we actually do is we try to minimize the distance, the L2 distance, between the input point and the output of the network. So the network is trying to regress the output towards the input. And this will be very important. And to see how this could be important, and maybe also to provide a bit more intuition, I will again draw a small picture. Oh, wait, maybe that's better. Okay. And how one typically draws these autoencoders is the following way. Both of these trapezies, or whatever, they represent the two parts of the autoencoder. So the first part is the encoder, the second part is the decoder. And what happens is that an input goes into the neural network. It comes from Rn. It passes through the encoder, then through the decoder. Out comes X twiddle, which again lives in Rn. And we want that X is approximately X twiddle. Like we train the network such that this holds. Now the crux is that the data in between has to pass through this bottleneck layer, it's called. So this is a layer of the neural network which is far thinner than the input or the output. And now remember that we regress the output towards the input. This means that the information of the input has to kind of travel through the bottleneck layer. And then, because the output is again approximately the input. So what the network, in order to minimize its loss, the network has to find a lower dimensional compression of the input. Okay, and now kind of as a byproduct of what we're doing, of the training, in the end, we can look at, let's call it T, just the image of the data matrix, just the image of the data matrix under the encoder. This will live in RL, so this is low dimensional, and it kind of still has to carry the information of the input data. And this embedding, it's called an embedding, and I will also refer to this RL as latent space. Okay, so that we could call this a latent embedding or whatever. This embedding we can actually use for whatever we want to do. We can use it for downstream applications in order to do faster downstream applications. We can use it for visualization, so that if we pick L equals 2, we get a nice two-dimensional representation of a high-dimensional data set. That's what we were starting out to do, right? Okay, but now we have this new construction, this autoencoder, and the question remains, how is this related to PCA? In particular, if we now come back to linear activation functions, so if a neural network is basically just a linear map, which can be learned by the data, can we somehow recover PCA? Because that would be nice, because then we could argue that PCA is an edge case of autoencoders, or autoencoders are actually a generalization, because otherwise there could be two completely different objects. But luckily, and otherwise I probably wouldn't be saying this, this is actually the case. We can show that linear autoencoders and PCA are closely related, and I will do this in 2 steps. I will formulate the first lemma. I will not go into great mathematical detail, but I will try and provide you an intuition for why this actually holds. Okay, the lemma reads as follows. A linear autoencoder, I will abbreviate autoencoder by AE, okay, which a linear autoencoder ED, encoder and decoder, is optimal. It's optimal given the data, so optimal in the sense that it minimizes this objective, if and only if ED is of the form okay, AW and W transpose A inverse for W the PCA solution. Okay, I will spend a little bit of time on this W in a second. Is the PCA solution, and A is an invertible matrix. Is in GL of L. And what do I mean by the PCA solution? Remember that PCA basically acts like an orthogonal projection on lower dimensional onto a lower dimensional space, and W is the matrix such that PCA basically acts like W transpose W is the projection. Okay, is this clear or is it not clear? Is this how you were talking about PCA?
Differentiation.
Okay, differentiation, yeah, but okay. Okay, I mean, PCA is just an orthogonal. Okay, I saw a thumbs up, then that's okay. Okay. Okay, before I start a sketch of this proof, just a quick intuition. If we now look at this autoencoder, we need to apply D after E. What happens is that the A cancels if we actually apply the autoencoder, and we are left with exactly this projection. But this is like a high-level intuition why this could actually work. So the autoencoder in latent space has a degree of freedom, which is like an invertible matrix, because the decoder can actually apply the inverse of this matrix. So the actual loss is invariant to applications of an invertible matrix. Okay, this is like an intuition. Okay, and we start with the proof that ED be optimal. And then one can show that under reasonable assumptions on the data, so that you use. So I think you need to assume here that all of these singular values of the data matrix are unique, but I think this does not really restrict generality, in practice at least. Because what we then can say is then the rank of D after E is maximal. Okay, the rank of D after E is upper bounded by the minimum of the rank of D and the rank of E. Both of them are upper bounded by L, but under reasonable assumptions, you can actually achieve the upper bound by an optimal autoencoder. Okay, and now we construct another matrix B as follows. Let B be the matrix which has an orthonormal basis of the image of DE. Okay, the image of ED is a linear vector space, or is a vector space, and we can pick an orthonormal basis of this as rows. Then we claim that in this case, DE after E, so the neural network basically, is already given by B transpose B. And why is this the case? We have to think a bit about a functional analysis here, or linear algebra, or whatever. Okay, if this was not the case, then picking as as ED, picking B transpose is better in some way than picking DE. Why is this? And this would be a contradiction to the assumption that ED is optimal. And why can we actually conclude this? This is because L2 is a Hilbert space, and we know that in Hilbert spaces, the map which minimizes kind of, if you have a bunch of points and you want to look to where's the point on the linear subspace of the Hilbert space, or the subset of the Hilbert space, which has the minimal distance to the other point, then it's given by the orthogonal projection. Okay, and correct. So yeah, we would find like a a better lower dimensional embedding. Okay, and this is a contradiction. And okay, and what have we seen now? Okay, and from this we can actually conclude also that dE is already W transpose times W. So the PCA solution. And this is because you can also think of the PCA solution as looking at the optimal orthogonal projection to a lower dimensional space. And because this is already an orthogonal projection, and by the optimality assumption, we know that this already holds. And what we've in particular seen now is that the PCA solution also minimizes the autoencoder objective, which is here, right? Somewhere here. Okay, and this concludes one implication, because we've seen that if we pick the PCA solution, and okay, we can multiply by an invertible matrix because this cancels out, then we get an optimal autoencoder. And for the other way around, you start exactly like we did here, and you arrive at dE equals W transpose W, and then you need to do like a bit of math in order to show that you can actually, from this, conclude that you can kind of split the product here after some math and see that dE is the same as, what did I say? W transpose A inverse and A W. Okay, the details here are not that important. You can find them in the first appendix of the paper I've mentioned at the beginning. The important thing to remember is that linear autoencoders kind of learn PCA, if just left on their own, up to an invertible matrix in latent space. And this has something to do with the actual objective we pick and with Hilbert spaces and that orthogonal projections, which is exactly what PCA does, kind of minimize distances to a lower dimensional linear space, right? Now we'll continue here, because we could still think, okay, but we still have this invertible matrix here, and this is not actually the PCA solution. So but we can kind of, if we have one more assumption or whatever, we can further restrict the choice of A, which is the following lemma. We pick an optimal autoencoder, and then we can represent it by such a pair, right? And then if the Frobenius norm of W transpose A and AW transposed, if this is minimized, so if they're both mutually minimized, then, or also you can also say if their sum is minimized, then this implies that A is actually an O of L, so it's either a rotation or a reflection. Okay, so and what we can do and how can we actually achieve, like if we're training an autoencoder, how can we achieve minimal Frobenius norm of the weights of the autoencoder, right? This is by doing regularization. I think you've talked about this. You can actually do, it's called weight decay here. So you just add a penalty on exactly this term. And what the optimization algorithm will do then, it will not just try and optimize the primary reconstruction loss, but it will also try and make the Frobenius norm of the network as small as possible. Okay, and then this means that if you just train an autoencoder with weight decay, with Frobenius weight decay, linear autoencoder, then you will reconstruct PCA upon like rotation or reflection of the embedding. Okay, and what we've seen, okay, and the proof is not very hard. You do an SVD, a singular value decomposition of A, and then you do a bunch of math, and then you can see it in the appendix. It's just basic transformations. And then you actually arrive at this result. Okay, I will not ponder on this too much. But Okay, now we've seen the basic idea of autoencoders and how we can think about them as nonlinear generalizations of PCA. But they are far more powerful, or can be far more powerful, because they can be nonlinear, right? Yeah. Yeah, I mean, I mean, you obviously, if the input has the same dimensionality, you can input it. But what the autoencoder learns is it learns kind of where the information in the data set sits. And if you put in another data set, then the information could sit somewhere else. I mean, when I say sit, yeah, but I think you know what I mean. So you can still input it, but right now I don't see how this would help you capture, yeah, because the information could be somewhere different, right? So it could be that you ignore actually so if you train an autoencoder on dataset A, you learn to ignore information at a certain spot, but for dataset B, this spot could actually where the important information sits. So it kind of you can still input it, but it's not going to give you reasonable embeddings, I would say.
Would be good to have a break at some point.
Yes, yeah, that would be a perfect time, actually. Now would be a perfect time for a break. I have like 10 or 15 more minutes. Questions or break, or what do you prefer? Yeah. Yes. Yes, yes. I mean, oftentimes machine learning is used by other fields of science, right? So in medical, in biomedical applications or something, you have high dimensional data, as I said in the beginning, and you kind of want to understand the data. So for example, you can kind of read genomes, or I don't know how it exactly works, and then you can put this in, you can kind of extract the data that is encoded by our DNA. And then you can take this data from sick and healthy patients, and you can hope to understand which gene, for example, makes a patient sick. And what you could do is you could train an autoencoder on the data, and then you could look at the low dimensional embedding. And then you could try and spot differences, right? You could try and this would be like an application in biomedical sciences. But yes, there's many more. I think later in the lecture, actually, we'll also see an application to LLMs, so you can understand where the information in larger language models sit. I would say, generally speaking, if you look at visualization, whenever you have a high-dimensional data set which you want to visualize, you can use autoencoders. And this can apply to any kind of field. Yeah. I mean, I don't know. I'm not sure I can answer this question, but maybe I can compare it to other dimensionality reduction methods. So usually, what you would do with PCA is you take the whole data set and you compute the principal components. And whenever you take one more data point into your data set, you have to recompute all of the principal components, right? You have to do the whole computation from the beginning. But if you train an autoencoder on like a data set, and afterwards you get new data, you can just put the new data into the trained model and you will get the embeddings or whatever, and you will not have to retrain the whole model. Yes. Yes. Yeah, I'm not sure I can answer this, but I think it depends. I will also talk about this in the second half. There's also other dimensionality reduction methods which are just parametric. They do not rely on neural networks, and they actually give you very well clustered data. So if you just want to cluster your high dimensional data, you could also use another kind of dimension. It's called UMAP, for example, or TSNE. Yeah, you know it, okay. So they give you well-clustered data. But we also wrote about this in the paper. You kind of tend to lose information about the higher, about the connectivity or whatever, or the higher dimensional topology of the data set. So yeah. So I think it heavily depends on the application, honestly. But maybe I think maybe Fred is better suited to answer this question because.
Well, the compression question, a big distinction is whether you need lossy or lossless compression. And we need both. So if we zip a file on our hard drive, we would like to have that lossless. Yeah? So, you know, if we unpack, we want our original information back. And for this, this kind of technique is obviously not useful. We usually accept lossy compression in images and in sound. And well, for images, the de facto standard are lossy compressions of the JPEG type. This is an encoder a little bit similar to doing standard PCA on local image patches. This is why you see sometimes when you heavily compress, you see these blocky artifacts in JPEG images. But there's more to it. There are a number of quantization steps involved. And for audio, as you know, MP3 and similar formats are very popular. So autoencoders could be better. Let's say if we know that we just want to compress human voice. And then, but these are data dependent. Yeah. So if you trained an autoencoder to compress spoken English, that would be different from an autoencoder that's supposed to compress all languages in the world. And you know, some languages in the world rely much more on guttural sounds or on clicking sounds, which are not very important in English. Yeah, so we now get into this rabbit hole of, well, this is data dependent, and how data dependent do you want to make it? Yeah, so in principle, autoencoders could achieve higher rates of compression. In practice, for images and for audio, it's not being used. And the postscript on the other question about images, so we, all of you have used Stable Diffusion, yeah, when you've prompted some model to create an image for you. And the Stable Diffusion, in fact, does happen in this kind of latent space. Yeah? So, and we will look at that in the lecture later. So this is like a very, very fancy version. It's much more than just autoencoders, but yeah, the concept does play a role. And I think you have more questions coming at you, Philip.
Uh-oh, okay. Yeah, yeah, you can. Yeah, okay. Yeah. Yes, it's a matrix product. So you can, the W, how it comes apart as it contains the principal vectors as rows. So this way you build a matrix and then you just do matrix multiplication. Yes. Yes, yes. Yes, you would not, if you were, okay, here, like this A in general is not just rotation, it can be any invertible matrix. You could also, you have rotation, you can also have stretching, but this would just be, so if you do weight decay, then you would just have rotation or reflection. And yes, this would not help you. You would not want to train, in my opinion, you would not want to train a linear autoencoder with weight decay just to recover PCA. This is not, there was just to like make the connection between PCA and autoencoders. But in general, like the autoencoder, you would use non-linearly.